Hey guys, if you're on the application problems and you're kind of stuck, please make sure you listen to this video. I'm just going to go through the examples that are in the book that are similar to these application problems, and hopefully that'll help get you started. So example 2 in the book is talking about finding an exponential model, and basically what it gives you is a set of data. Here it says it's a number of scooters sold in a number of years, and it lists 1, 2, 3, so the first 7 years and the number of scooters that they've sold. And what it asks you to do first is to draw a scatter plot of the data and then see if that exponential model is a good fit for the original data. So when it says draw a scatter plot of the data pairs x comma ln of y, basically what you're going to do, and you could do this in a table on your paper and then use a calculator, is type in, so you're going to have all your x values stay the same, so 1, 2, 3, 4, 5, 6, 7, whatever, and then instead of graphing the point 1, 12, you're going to take the ln of the y values, and that's going to be your new y value. And so that's what they did here in step 1, is they took the ln of 12 and they got 2.48. They took the ln of 16 and they got 2.77. And then they used their calculator and came up with this new set of data points, and then they plotted them, and what they're looking for is if these new data points make as close to a straight line as possible. So if you look at what they have here, they took their new points and they plotted them on a graph. Obviously you want to do as close to as accurate of a graph as possible. If you need to use a graphing calculator, that's fine. And then you're going to plot those points. Well, if you look at it, it makes almost a perfect straight line. So the answer to the part where it says, is it an exponential model a good fit? The answer is, of course it is. If it fits as close to possible as a straight line, then the exponential model is going to be good. And then once you establish if it's good or bad, you need to find an actual exponential model for the original data. So what you're going to do there is use the rules that we talked about earlier in the section in the actual notes, your y equals ab to the x, and choose 2 points from this data that you calculated. So here they used the point 1, comma 2.48, and then the last point 7 comma 4.56, and typically the first and last are going to be good ones to go through with, but it's your choice which points you want to use. Okay, and then all they did was they plugged it into an equation of a line. Now what I would suggest is following the steps that they use. This is point slope form, but if you want to find slope and then plug it in and find the y-intercept, however you want to do it is fine as well. But the reason point slope form is so useful is because it's a little bit different than writing just y equals mx plus b, because we're dealing with an exponential model, not a linear model. So if you notice what they did here is they went ahead and they wrote their point slope form. So ln of y minus their y value, okay, equals the slope that they found times x minus 1. And the reason we use ln of y here instead of just y minus the y is because we're talking about an ln of y type point. It's not the original y value. So then they went ahead and they distributed the 0.35x and they added 2.48 over, and then we're dealing with a log function, and you want to get the y by itself. So to get rid of an ln problem, you take e to both sides. So that's what they did here in the step 3. And then when you're dealing with something that's got 2 parts to it in an exponent, you can just split it and multiply them. So I just took e to the 2.13 times e to the 0.35 to the x. So notice here they just took these two things and they multiplied, and the reason they multiplied them is because of our exponent rules. If you multiply two things with the same base, you can add the exponents. Okay, and then they just used a calculator to figure out what these two numbers were. So e to the 2.13 is this 8.41, and then e to the 0.35, that's 1.42, and that's all to the x power. Okay, so this is the model, and this is the steps I'm wanting you to follow. So first, see if your new data that you come up with fits a straight line. If it does, then use this point slope form and then change it to your exponential form to come up with an exponential model. Okay, and the same concept applies to our power functions. But instead of doing x comma ln of y, you would do like what they did in the last example here. So example 5, where they do ln of x and ln of y, and the process is exactly the same. Plot the new data points, see if they make as close to a straight line as possible. If they do, then in a power function, you would use your y equals ax to the b and put everything in a point slope form, just like you did here. Notice that the only difference between this one and the last one is that when you have point slope form, you have ln of y minus y, and then slope, and then ln of x minus x, because you took the ln of the x and the y to plot those new points. All right? So use these two examples in your book. If you need to go back and look at them more, they're just a couple pages back. Follow those steps if you need it. Otherwise, you guys should be good to go.